welcome back to this week's algebraic graph theory seminar. This week we have Yufei Zhao to tell us about the equiangular lines and eigenvalue multiplicities.
Thank you, Tina, for the introduction, and it's a great pleasure to speak here in the seminar. So I will talk about equiangular lines and eigenvalue multiplicities. And this is a work that started a few years ago with a team here at MIT, and it's a problem that I'm still very much interested in today. So equiangular lines are configurations of lines in space. I'm mainly considering d-dimensional real space that all go through the origin and pairwise form equal angles. And the natural question is, what is the maximum number of such lines you can place in a given dimension? In 2 dimensions, it's pretty easy to visualize, as you see in the slide here, that the maximum number is 3, these 3 lines. And you cannot put 4 lines in that still all make the same angles with each other. But even in 3 dimensions, already a little hard to visualize. We do know the answer. The answer is 6, coming from the 6 main diagonals of a regular icosahedron. This problem has been solved exactly for small dimensions. So in finitely many dimensions, we do have some general bounds for higher dimensions. A really nice linear algebraic method proof by Gerson in the 70s shows this upper bound of d plus 1 choose 2. It was somewhat surprising when Duquesne came up with a matching lower bound that grows quadratically in the dimension. So that in high dimensions, we know the upper and lower bounds up to a constant factor apart. There have been some minor improvements on these bounds over the years, but roughly this is where our knowledge stands. I want to point out that in all the lower bound constructions giving quadratically many equiangular lines, the pairwise angles all approach 90 degrees as the dimension goes to infinity. So the problem that I want to focus on in this talk is what happens if you do not let the angles change? Well, consider equiangular lines with a fixed angle. We fix an angle, somebody gives you an angle theta. It will be convenient to parameterize by the cosine of the angle. So we'll look at this alpha, which is the arc cosine of the angle. So it's the cosine of the angle. And we would like to know what is the maximum number of lines in d-dimensional real space, all passing through the origin with pairwise angle arc cosine of alpha. And mainly we'll fix on the regime where alpha is fixed, the angle is fixed, and the dimension goes to infinity. But here's the first surprise. In contrast to the case of unrestricted angles, where the number of lines is quadratic in the dimension, if you fix the angle, the number of lines actually grows linearly in the dimension. So there's a pretty big contrast, this problem with fixed angle versus unrestricted angle. Given that a natural problem then is to determine what is this limiting ratio, and what is the factor in front of the linear growth. Let me tell you a bit about the history of this problem. So while equiangular lines have been studied for quite some time, the specific version of the problem with a fixed angle, the first paper on it was by Lemons and Seidel in the 70s. It turns out that for this problem, each angle has its own features, and it's fine to consider it a different problem for each angle. Turns out the simplest, the interesting case is when alpha equals to 1/3. So we're looking at the common angle arc cosine of 1/3. In the paper Lemons and Seidel, they solved the problem for every dimension, and in particular, for large enough dimensions, the answer is 2 times d minus 1. The next interesting case, being alpha equals to 1/5, was solved about a decade and a half later by Neumayer. And he determined this answer for sufficiently large dimension, and turns out to be this expression here, roughly 3d over 2. Neumayer writes in his paper that the next interesting case will require substantially stronger techniques. And he has a specific reason for making this claim that I will explain in a second. Progress on this problem stalled for some time, and there were some revived interest more recently due to Book, who showed that indeed, perhaps as suspected, the number of lines grows at most linearly in the dimension when you have a fixed angle. So this is in a sharp contrast to the case of unrestricted angles where the growth is quadratic. So we wish to determine this limiting value, the coefficient in front of the linear growth. And in particular, you can ask for which, so there's a function of alpha. So which alpha maximizes this coefficient? Now, perhaps you would suspect, given something I told you earlier, namely that in configurations with quadratically many lines, the angles go to 90 degrees, corresponding to alpha approaching 0. So you might suspect that as alpha gets closer and closer to 0, you might get more and more lines. But actually, that's not true, and this is quite counterintuitive. So in the paper by Bala, Drexler, Kivas, and Sudakov, they showed that this coefficient is actually maximized at alpha equals to 1/3. So all the other values of alpha, the answer is strictly less than 2. Subsequently, Zilin Zhang and Sasha Poliansky determined this limit when alpha is bigger than 0.196. And so there's some specific value here which come from spectral graph theory. And actually, they proved an interesting theorem in spectral graph theory that allows you to characterize when is the set of graphs with spectral radius less than lambda characterized by finitely many forbidden induced subgraphs. And they show that that is the case if and only if lambda is less than some critical value, which corresponds to this angle here. And it turns out that is also the barrier that Neumayer mentioned in his paper from the 80s. The reason he said the next interesting case will require substantially stronger techniques is that this line of techniques having to do with this approach of using spectral graph theory, but a very specific approach, actually hits a roadblock. And John and Poliansky specifically identify where that roadblock is. Despite that, we were able to completely solve this problem. And we determined this coefficient for all values of alpha. So in the first part of the talk, I will tell you what the theorem is. What is the answer? So given alpha, how does one determine this limiting coefficient? And then I will discuss connections to spectral graph theory. So this work was done with this wonderful team. So at the time we did this work, all of them were at MIT. The Zilin Zhang was my postdoc. He's now an assistant professor at Arizona State. Jonathan Tidor, my PhD student, just graduated and will be moving to Stanford this fall. Yuan Yao was an undergrad, and Shengtong Zhang was also an undergrad at the time of this work. So both of them have started or will be starting graduate school. So let me tell you what is our main theorem. So recall the problem is to determine for a fixed angle alpha in high dimensions d, what is the maximum number of lines in d dimensions with pairwise angle arc cosine of alpha. And first, it's a special case when the number alpha has the form 1 over an odd integer. We determine the answer to be this expression, which is consistent with some of the special cases, alpha equals to 1/3, alpha equals to 1/5 that you saw earlier, continues that pattern. So for large enough dimensions, we determine the answer, this expression here, roughly kd over k minus 1. But actually, we determine the answer exactly without any error terms, provided that the dimension is large enough. For other angles, we can also tell you the answer, but I will require a bit more definitions. So given a fixed alpha, I will take a change of variables, setting lambda to be this expression, 1 minus alpha over 2 alpha. The reason is that this lambda will play an important role later on when we convert this problem to a problem about spectral graph theory, and lambda will correspond to some eigenvalues. So it's important to have this change of parameters here. We'll define a quantity called the spectral radius order. So the spectral radius order, k of lambda, is defined to be the minimum number of vertices in a graph whose top eigenvalue is exactly lambda. In this talk, whenever I talk about eigenvalues of a graph, I'm always referring to that of the adjacency matrix. Okay, so let me repeat this definition. Somebody gives you a lambda, and I want to find the smallest graph, smallest in terms of number of vertices, whose top eigenvalue is exactly lambda. And I output that k. So for example, I can search through all graphs in increasing number of vertices. And the first time I see a graph with top eigenvalue exactly lambda, I stop and I output the number of vertices. It could be that perhaps no graph has top eigenvalue exactly lambda. For example, when lambda is not an algebraic integer, that is the case, in which case I output k equals to infinite. Our theorem says when k is finite, then this quantity, the maximum number of equiangular lines with a fixed angle in high dimensions, is given by this expression here. So this k from the spectral radius order divided by k minus 1 times d minus 1, so take the floor of that expression, for all sufficiently large dimensions. When k is infinite, we know that the answer is d plus little o of d. And so with an error term that is sublinear. Okay, so that's the main result. Let me also say a bit more about the definition spectral radius order that we saw in the previous slide. Just to give some more examples, when alpha is given, for example, alpha equals to 1/3, then by this expression relating lambda and alpha, we can derive that lambda equals to 1. So which graph has top eigenvalue exactly 1, and among those, which one has the smallest number of vertices, turns out to be a single edge, and it has 2 vertices, so we record k equals to 2. Likewise, when alpha is 1 over an odd integer, lambda is equal to a positive integer, and k then is lambda plus 1. When lambda equals to 3, the smallest graph with top eigenvalue 3 is a clique of 4 vertices, so k equals to 4. You can have other interesting values. So for when alpha is this value here, lambda is root 2. And the first graph, the smallest graph with top eigenvalue exactly root 2 is this 2-edge path, which has 3 vertices. So we set k equals to 3 here. Okay, so that's a further explanation of the definition of the spectral radius order. So that's our main result. Let me comment a bit about quantitative bounds. So here we need sufficiently large dimension. Our proof requires a bound roughly double exponential in the parameters. In this case, 2 to the 2 to the k to roughly k log k. And we conjecture that actually maybe polynomial in the parameters is enough. So there is still a large gap in what we can prove and what we believe the truth is. When does this bound kick in? And this double exponential parameter dependence will come up later on in a result that we'll prove about spectral graph theory, where there's a lot of interesting open problems about quantitative bounds over there. So let me pause for a bit and see if there are any questions about the main result on equiangular lines. Okay. A key result in our proof of this theorem is a new result in spectral graph theory. And it tells you something about eigenvalue multiplicity. So we prove that a connected bounded degree graph always has sublinear second eigenvalue multiplicity, sublinear in the number of vertices. Here, we're always referring to the adjacency matrix, although other matrices, such as a normalized adjacency matrix for random walks, could also be interesting. But for the purpose of this application, we'll always be looking at the adjacency matrix. More precisely, we showed that a connected n-vertex graph with maximum degree delta has second largest eigenvalue with multiplicity at most on the order of log delta times n over log n. I'm usually thinking of delta as fixed. So here the bound is n over log n. I'll mention some remarks about the tightness of this bound. And briefly, I do not know how tight this bound is. And it's an interesting open problem to try to improve this bound. And this log is the reason why we require double exponential dependence in the dimension before the theorem kicks in on the previous slide. I think this is an independently interesting theorem in spectral graph theory that it's worth its own attention. In spectral graph theory, most results concern the spectral gap. So there's been a lot of work understanding the difference between the first and the second largest eigenvalue. And because the spectral graph plays a really important role in mixing and expansion, and it's a really fundamental concept. Whereas eigenvalue multiplicity has not really been studied. And our result here is a first general bound on eigenvalue multiplicity for general classes of graphs. And I hope that this work will bring more attention to this problem and see what other applications it has. So far, I've told you two seemingly different things. On one hand, equiangular lines with a fixed angle. On the other hand, a theorem about eigenvalue multiplicity. And so in the next part of the talk, I want to explain how these two problems are related to each other. Now, this connection is quite classical. And in fact, in this wonderful textbook on algebraic graph theory by Chris Gossel and Gordon Royal, there's a whole chapter on equiangular lines. And it is mentioned that equiangular lines is one of the founding problems of the subject. So I want to explain this connection in the context of our work. Starting with a configuration of equiangular lines, we can form a geometric configuration of unit vectors by picking a unit vector along each line. There is a choice here, one of the two orientations of the vector, but for now, pick an arbitrary one. With this configuration of unit vectors, we can form a graph. Now, the vertices of this graph are the vectors. I put in an edge if they form an obtuse angle, and a non-edge if they form an acute angle. Because we start with a configuration of equiangular lines, there are only two possible angles between the vectors, namely theta and 180 minus theta. Right, so this graph encodes that combinatorial information. Given a list of vectors, v1 through vn, we can form a grand matrix. This is a matrix of inner products. Now, this matrix is positive semi-definite. It also has rank at most d because we started with vectors in d dimensions. Because of what I said earlier about this configuration of equiangular lines, and in this grand matrix, all the diagonal entries are ones, and all the off-diagonal entries can only be plus minus alpha. So this grand matrix is completely determined by the combinatorial data of this graph. And we can rewrite it in terms of the combinatorial information of the graph. The formula turns out to be as written here. So I is the identity matrix, A sub G is the adjacency matrix of this graph up here, and J is the O1's matrix. And from this grand matrix, we can also recover the geometric configuration up to isomorphism. So the problem is losslessly converted to a problem about graphs. And so whereas we started with a problem about equiangular lines, it turns out to be equivalent to the following problem about graphs. Given alpha and d, some parameters, we wish to find a graph G with a maximum possible number of vertices n, such that this matrix here is positive semi-definite and has rank at most d. Given a configuration of equiangular lines, we can find a graph, as I told you, satisfying these properties. But also conversely, if you have a graph satisfying these properties, you can factorize the grand matrix to recover your geometric configuration. This equivalent formulation also provides an easy way to explain examples. Rather than giving you a list of vectors and their coordinates, which might be quite cumbersome, it's much better to tell you what the graph looks like. So for example, to show that there exists a configuration of 12 vectors in 9 dimensions, all of whose pairwise angles are arc cosine of 1/5, instead of telling you the coordinates of these vectors, which I will not do, I will just tell you this graph. And it turns out this graph is, as shown, it's a disjoint union of 4 triangles. And if you look at the matrix associated to this graph, this matrix is positive semi-definite, that one can check, and also has rank 9, which one can also check. So it's a grand matrix. And by factorizing this grand matrix, you can recover a configuration of 12 vectors in 9 dimensions, giving an equiangular lines configuration. So this technique allows you to show a lower bound, which matches our upper bound. The more interesting direction is to prove the upper bound. We wish to upper bound n. The proof starts like this. Starting with n, well, we have an n by n matrix, so we can use the rank nullity theorem to write n as the sum of the rank plus the nullity of the grand matrix. The rank we knew is at most d, and for the nullity, we can we could write the grand matrix as this expression here. Note that J is the O1's matrix. So we can factor out J by losing at most 1. Now this expression here, the nullity, well, it's the multiplicity of lambda as an eigenvalue of the graph, of the adjacency value of the graph. So if you rewrite this expression, you see that it's the same as lambda, multiplicity of lambda as an eigenvalue. So this gives you this connection between equiangular lines and eigenvalue multiplicities. Now, since the matrix is PSD, turns out that if lambda is an eigenvalue, then it must be either the largest eigenvalue or the second largest eigenvalue. Okay, there's a short argument here, but roughly speaking, we know that this is PSD. If you knew that this expression without J is PSD, then that would tell you that lambda has to be the largest eigenvalue. But adding J, a rank 1 matrix, shifts all the index by most 1. So lambda can be the first or the second largest eigenvalue. Turns out the largest eigenvalue is the easy case to analyze, and it happens to also be the equality case. It corresponds to many repeated copies of a small graph. And the hard and interesting part of the problem is to rule out the possibility that lambda is the second largest eigenvalue. So let me recap, and then I'll pause and take questions. We started with a configuration of equiangular lines in RD, n lines, and we used to form a configuration of unit vectors. This allowed us to form a graph where the edges of the graph correspond to the 2 possible angles, acute versus obtuse, that come up, and it turns out to encode all the combinatorial data in this geometric configuration. By a rank nullity argument, we were able to show that n is at most d plus the multiplicity of lambda as the eigenvalue of d of the graph plus 1. And it turns out that the optimal configuration for large enough d is when G is a disjoint copies of a fixed graph whose top eigenvalue is exactly lambda. So this is where the definition of spectral radius order came in. You want to find a fixed graph of smallest possible size whose top eigenvalue is exactly lambda, and the optimal configuration in large dimensions turns out to be repeating this graph. The hard part of the proof is to rule out the possibility when lambda is the second largest eigenvalue of G. And we'll assume from now on that G is connected. So there's a short argument reducing to this case. And the goal is to show that the second largest eigenvalue of G occurs with small multiplicity. And that's the plan going forward. So let me pause and take some questions. So I already see one question in the chat, how to explain the quadratic lower bound. Yeah, so the quadratic lower bound corresponds to different choices of G. It turns out when the dimension is small, there can be other and better configurations, usually involving nice algebraic graphs like strongly regular graphs. Right? So these highly symmetric graphs turn out to actually be better choices when the dimension is small. And in that case, lambda actually is the second largest eigenvalue. So that's what explains the small dimension cases. And it's only when the dimension gets large, the second eigenvalue multiplicity bound kicks in and rules out possibility for lambda being the second largest eigenvalue in the optimal configurations, that G becomes this much more structured example of taking disjoint copies of some fixed small graph. Yeah, that's a great question. Are there any other questions before I move on? Feel free to unmute yourself and ask a question. Okay, so the next thing we would like to do is to show that G has small second largest eigenvalue. So here's the question. Must all connected graphs have small second eigenvalue multiplicity? The answer is no. For example, a clique on k vertices has top eigenvalue once and eigenvalue -1, should be -1, k -1 times. But it turns out that not all graphs can arise from equiangular lines. When we constructed the graph from a configuration of equiangular lines, we had to make a choice on which direction each unit vector points in. And turns out you can make a different choice. And it matters here that by switching a vector from V to its negative, we end up switching the graph in the following sense. All the edges and non-edges get reversed around the vertex. An important step towards the solution is the following observation that was proved in Bala, Drexler, Kivas, and Sudakov, essentially following from the arguments there, that for every fixed angle, one can switch this graph so that it becomes bounded degree. And for every alpha, there exists a delta, so that by choosing the vectors appropriately in which one of the two directions, making a good choice, you can ensure that the graph has maximum degree at most delta. A more recent work by Bala shows that you can actually take delta to be on the order of alpha to the -4, and this bound is tight. So the previous argument used Ramsey theory, which incurred an exponential dependence, but it turns out that you don't need that. So knowing that, we can then focus on the setting of bounded degree graphs. So this is where our resultable second eigenvalue multiplicity comes in. So we showed that a connected n vertex graph with maximum degree at most delta has second largest eigenvalue with multiplicity at most on the order of n over log n. And this is enough to complete the picture. So once you know the second eigenvalue cannot occur with high multiplicity, it rules out the possibility of lambda being the second largest eigenvalue. It's not competitive compared to the case of lambda being the top eigenvalue, which then corresponds to the construction with disjoint copies. And this completes the picture. So for the rest of the talk, I want to focus on this theorem here, which I think is interesting intrinsically, but also lots of open problems about quantitative bounds. There isn't really anything special about second largest, as in I can replace the number 2 by any other fixed number. So the 10th largest eigenvalue also has multiplicity at most n over log n. So the dependencies change. And more generally, the proof also shows, informally speaking, that you cannot have too many eigenvalues near the top of the spectrum. Now, let's look at this theorem statement here. So there are various hypotheses and adjectives in the statement, and I want to explain why all of them are necessary. Here are some near-miss examples. By erasing one of the adjectives, the theorem is false. So for strongly regular graphs, such as complete graphs, they have high second eigenvalue multiplicity, linear multiplicity, in fact, but they can never be bounded degree. You can get other eigenvalues with high multiplicity. For example, this graph here, by attaching a path of length 2, by attaching 2 leaves to every vertex, we can get eigenvalue 0 with linear multiplicity. Because I can attach a gadget, let's say put +1 and -1 on 2 vertices and 0 on all the other vertices, I can get an eigenvector, and I can move that eigenvector around. But 0 is never the second largest eigenvalue, it's one of the middle eigenvalues. In fact, later on, I will even show you an example where the smallest eigenvalue has linear multiplicity. So our theorem is really about one of the top eigenvalues. It's not about the middle eigenvalues, it's not about the smallest eigenvalues, it's about the top eigenvalues. If you drop the connectivity hypothesis, you can also easily come up with counterexamples, such as this graph here. It has top eigenvalue with linear multiplicity because the spectrum is just repeated however many times you repeat the graph. What about quantitative bounds? So what should this maximum second eigenvalue multiplicity, how large can it get? So we show this upper bound of n over log n. I'm really thinking of delta as fixed, the maximum degree as fixed, but of course the dependence on delta is also interesting. How does one construct lower bounds? Actually, it's already kind of tricky. So how would you come up with graphs with high second eigenvalue multiplicity? Now, it's pretty hard to get eigenvalues to coincide. As in, if you just take an arbitrary graph or a random graph, there's a phenomenon known as eigenvalue repulsion. Eigenvalues really don't like to be close to each other. So they collide for a reason. And one way to get them to collide is through symmetries. So graphs with a lot of algebraic symmetries, such as coming from Cayley graphs, that is one way to get high eigenvalue multiplicity. So one way to construct such a graph is to take a group that's highly non-abelian, so what Gowers calls quasi-random groups. For example, if you take a 4-regular Cayley graph on PSL2Q, that's one way to get high eigenvalue multiplicity. That example gets you around cube root of n. In a follow-up work with Milan Hyman, Carl Schreikraut, and Shentong Zhang, the 3 undergrads at MIT, we managed to construct an infinite family of bounded degree graphs where the second largest eigenvalue is at least square root of n over log n. Okay. This also uses group symmetries to get eigenvalue collision. And we think that this method hits a barrier at around root n. Just because if you give me a group of order n, all of its irreducible representations have dimension at most square root of n, because sum of the dimension squares has to add up to n. So getting beyond root n will require new ideas. Just a very quick word about the construction in case you're curious what this graph is. Okay, so let me quickly say it, but not go into detail. So we start, so there are two steps in the construction. The first, we start with a Cayley graph on the group of affine transformations of FQ, generated by a multiplicative generator and an additive shift. And then we convert each edge of the second type corresponding to an additive shift to a path of length log q. Okay, so this gives you a graph of bounded degree with high second largest eigenvalue multiplicity. It's a really interesting open problem whether one can prove an upper bound of the form n to the 0.99. If you can do that, then it would imply that our equiangular lines with a fixed angle theorem that we saw earlier would work for dimensions at least starting from polynomial in K rather than double exponential as we do now. Let me mention some other known results. For expander graphs, if you assume some expansion or equivalently some spectral gap on the graph, then our proof technique gives you a slightly better bound n over log n rather than double log n. This really interesting work by Lee and Makarachov showed that for non-expanding Cayley graphs, namely those graphs where balls have a bounded doubling ratio, for non-expanding Cayley graphs, the second largest eigenvalue actually has bounded multiplicity. So in particular, if you take a graph on the abelian group or a nilpotent group of bounded rank, then you cannot get high eigenvalue multiplicity. If you start with Cayley graphs, you must start with highly non-abelian and expanding Cayley graphs. One reason this theorem is interesting is that the proof builds on some important theorems from Riemannian geometry, starting with Gromoff's theorem, his famous work showing that a group of polynomial growth has to be virtually nilpotent, as well as later work by Kolding and Minicozzi, which resolve a conjecture of Zhao on the space of harmonic functions, and Kleiner's proof of Gromoff's theorem. Building on those techniques, Lee and Makarachov were able to show this theorem here, which in some ways quantify some of the earlier works. If you restrict to regular graphs, and more generally, instead of the adjacency matrix, if you look at the normalized adjacency matrix corresponding to simple random walks, then the recent work of McKinsey, Rasmussen, and Srivastava show that you can get a bound of n over polylog n. So they build on our work, but were able to use new ideas to improve the bound. A couple comments. One is that even though there's a quantitative improvement here, it does not imply an improvement for equiangular lines, because for equiangular lines, we really do need the result for adjacency matrix of general irregular graphs. Another is that their work introduces some interesting ingredients, which actually proves a new result about simple random walks. They show that a simple random walk of length 2k, a closed walk, a typical closed walk in such a bounded degree graph, typically covers a polynomial in k number of vertices. So a prototypical simple example of this is that if you do a simple random walk on an integer line, then typically you cover around square root k vertices, but this turns out to be true in general for bounded degree graphs. I mentioned in an earlier slide that there were some lower bound constructions that we came up with. For irregular graphs, we were able to construct lower bound roughly root n, and for irregular graphs, we found a construction for Cayley graphs with second eigenvalue multiplicity around n to the 2/5. Still, we can't quite get root n, but I think one perhaps should be able to. Okay, so let me say a bit about the proof idea. So this is the meat of the proof. So showing that the second largest eigenvalue has sublinear multiplicity. The proof is not long. It's about a couple pages in our paper. And I'm going to fit the ideas on this slide. So you're not expected to follow all the details, but I want to illustrate one key idea. So we want to show that the lambda2 multiplicity in G is at most on the order of n over log n. We start with G, and what we'll do is take out a net. So a net, as in like an epsilon net, is a set of vertices where every vertex is close to one of the vertices of the net. So R is around log n, and we'll be able to take out a net, and the net will not be too big. Right? So net is a size roughly n over R. And the resulting graph is H. So poke some holes in this graph. And the key observation is that this procedure, removing the net from a graph, must significantly reduce the spectral radius. So this is not hard to prove. It can be proved by analyzing, by counting closed walks, but it's a key idea, it's a key observation in this proof. In particular, we show that if you look at the local S-ball, S is around log n. If you look at the local S-ball, it has spectral radius significantly reduced from lambda. Yeah. So lambda is the second largest eigenvalue of G, which means that for pretty much all the vertices, if you look at the local ball, the spectral radius of that ball should be at most lambda. It could occasionally be higher, but that can't happen too often. And this step here says that by poking some holes, the top eigenvalue must drop substantially. We will bound the second eigenvalue multiplicity via moments. Of course, the moment method is pretty standard in spectral graph theory, and we use that here. But the key idea is that noticing net removal reduces spectral radius. So here's what we wish to bound: the multiplicity of lambda in H, the adjacency matrix of H. And by looking at the 2s moment of H, which is also the trace of the 2s power of the adjacency matrix, on one hand, by dropping all the terms which are not lambda, we can get the slower bound, only keeping the terms that are exactly lambda. On the other hand, we also know that this expression counts closed walks of length 2s in H. Well, what does a closed walk of length 2s in H look like? I start from somewhere, and I have to walk 2s steps and return to where I started. So that walk cannot wander distance more than s away from where I started. It must stay in the ball of radius s. Right? So if I start at the center, I can't wander too far, or else I don't have enough time to come back. And so the number of such walks comes from analyzing the adjacency matrix of this ball. And in particular, I can upper bound it by the spectral radius of this ball raised to the 2s power. So we can bound the number of closed walks of length 2s starting from a vertex V by the spectral radius of the radius s ball around V in H. But we just said that that ball has a reduced spectral radius because of the net removal lemma. Now, comparing the left-hand side to the right-hand side, you see that there's a reduction here, and that reduction will allow us to deduce a bound on the second eigenvalue multiplicity. This is for H. Now, H was obtained from G by removing a small net, and we know that from the Cauchy eigenvalue interlacing theorem, removing a vertex from a graph, the effect on the spectrum is that the resulting spectrum interlaces with the original spectrum. So the eigenvalue multiplicity cannot change by more than a number of vertices that you remove. So if you start with some number of repeated eigenvalues by removing some, the multiplicity can drop, but not by too much. Okay, so that's the proof sketch. And so if you plug in all the appropriate parameters and work out these bounds, we get n over log n. So the rest of this talk will be mostly remarks about this proof and its extensions. So first of all, the proof is analytic in nature. I think we do some inequalities analyzing the moments. So the proof can give you some room for error. It bounds not just the second eigenvalue multiplicity, but also bounds the approximate second eigenvalue multiplicity, showing that there is at most n over log n eigenvalues, including multiplicity, within a small window around the second largest eigenvalue. So with Hyman, Spherical, and Zhao, we gave a construction showing that this statement here is tight. So if we construct a graph where there are lots of eigenvalues very close to the second largest eigenvalue. And this graph is interesting in that it's a combination of an expanding graph and a non-expanding graph. You start with a 3 regular expander, do some work on it, and then eventually elongate each edge to a path. In fact, there's several parallel paths. So it's a mixture of expansion and non-expansion, and that's part of the difficulty in trying to improve the bounds. Somehow a better proof may need to understand expansion and non-expansion separately. Okay, so this construction also shows in some sense some limitations of the trace method. So perhaps one cannot improve the bound by just locally modifying the proof, but one needs some significantly new ideas. Okay, so that's a comment about the proof. Okay, in the remaining few slides, I want to talk about some variations and extensions of this work. So first, this work can be viewed more generally in the context of spherical codes. So given a subset of the reals, a subset, we call this L, say an L code is a subset of unit vectors, a set of unit vectors whose pairwise inner products all lie in L. And let's write n sub L of D to be the size of the largest L code in D dimensions. So this concept encapsulates many classical problems from coding theory. So the classical notion of a spherical code is a set of points on the unit ball, on the unit sphere, so that they're pairwise separated by some angle theta. We want them to be not too close to each other. And that's exactly the notion of an L code, where L is the interval from -1 to cosine theta. So for example, the problem of kissing number, give you a unit ball, how many other balls can you place around it? That corresponds to theta equals to 60 degrees. Sphere packing bounds in high dimensions, actually the best known such bounds come from first proving the bound on spherical codes, and then using an argument to translate that bound to Euclidean sphere packing. So this was the approach taken in the 70s by Kapatiansky and Levenstein, and still it gives the best exponential rate to the state. Of course, you know that there's some exciting recent work by Marina Vyarzovska that won her Fields Medal, understanding sphere packing dimensions 8 and 24. And there are also interesting problems about kissing numbers, which were solved much earlier, but in high dimensions, in sufficiently high dimensions, these linear programming bounds, which used by Kapatiansky and Levenstein, are the best tools to understand high dimensional packing. And this is a general phenomenon, even for variants of this problem, such as error correcting codes, binary error correcting codes. The best tools that we know in high dimensions are all linear programming, which also is the bound that used by Vyarzovska in dimensions 8 and 24. Our problem can also be cast in this slide, where L is now 2 values, minus alpha and plus alpha. And one way to view our work in this context is that we are able to go beyond what linear programming bounds can give. So this is a demonstration of a technique beyond linear programming bounds for a high dimensional design problem. Well, you can ask, what about for other values of L? The book showed that when L consists of a set of negative numbers bounded away from 0, as well as a single positive number, right? So this is the picture, then he showed a linear upper bound. For fixed L, the upper bound for this L code is at most linear in D. So Bala director Kivash and Sudakov extended Book's result to show that if you have K positive values, then the upper bound is at most D to the K. And in general, this cannot be improved, as in there are specific values of alphas so that this bound is saturated up to linear factor. So we do not know in general what should be the linear factors here, and that seems to be a difficult problem. So we explored that problem in the following special case of spherical two-distance sets. If you fix two possible angles, one acute angle and one obtuse angle, and ask what is the maximum number of lines, so maximum number of unit vectors with only those two angles allowed. Grows linearly if you only fix one acute angle. So what should this number be? So in our work, so this was a follow-up work from our Equiangular lines paper, we conjectured a limit in terms of now eigenvalues of signed graphs. So previously for Equiangular lines, the answer was in terms of eigenvalues of simple graphs. And here, turns out signed graphs play a key role. It's a little involved to say exactly what the conjecture is, so let me not do that, but just mention that we were able to solve the problem in some special cases. So we were able to solve it in the case when alpha is strictly less than 2 beta, as well as combining with a later development by Zhao and Poliansky, solve the problem in this setting. There's some funny constant here, and it turns out that Zhao and Poliansky solved a interesting problem in spectral graph theory of signed graphs, where this number is a barrier. The conjecture is open in general, and I would say that this is a state of things corresponding to where equiangular lines with a fixed angle sat before we started our work. And part of the difficulty why we cannot finish this problem right now is that the key step earlier on sublinear eigenvalue multiplicity is false for signed graphs. So I can have you a signed graph whose top eigenvalue has linear multiplicity. As an example, here is a bounded degree graph. Okay, so I've drawn it with a 6 cycle, but you can replace 6 by any number. So take a large cycle and glue some gadgets. This is a bounded degree graph whose most negative eigenvalue multiplicity is linear. If you put a -1 on every edge, then it becomes a signed graph whose top eigenvalue has linear multiplicity. And that's a major obstacle to our method. So we do not know how to get around that. Okay, so I only have a couple more slides to go. Let me tell you just a big framework picture on how we think about this problem. As in our work on equiangular lines and subsequent work on spherical two-distance sets, there seems to be 3 main steps in understanding this problem. First, we wish to understand forbidden local configurations or forbidden subgraphs. For example, using that the grand matrix is PSD, we can tell you that some configurations of angles just cannot occur. It would break PSD-ness. And using these local configurations, then we appeal to arguments from graph theory, in particular Ramsey theory, to understand some global structure of the graph. In the case of equiangular lines, we show that the graph has bounded degree. Well, it can be made into a graph with bounded degree. In the case of spherical two-distance sets, we end up showing that the graph is basically a complete multipartite graph with a bounded number of parts, and symmetric difference that with a graph of bounded degree. So this is a structural description of what such a graph should look like. And the third step appeals to spectral graph theory, in particular eigenvalue multiplicity, such as our result showing that a bounded degree connected graph has sublinear second eigenvalue multiplicity. On the previous slide, there was some number 2.019. So the latest result on spherical two-distance set rely on this new work of Zilin-Zhang and Sasha Polyansky, and they solved this interesting problem in spectral theory of sign graphs, showing that if you look at the collection of graphs, a family of sign graphs whose largest eigenvalue is at most lambda, and ask, can you describe this family by forbidding a finite collection of induced subgraphs? They show that the answer is yes, if and only if lambda is less than this critical number, 2.019. So, okay, and that is the problem that they solve, and this translates into a corollary for spherical two-distance sets using our framework. Okay, so these are roughly the three-step plan in all of our successful approaches. And I hope that this approach can be applicable to other problems as well. Let me also mention, just for general interest, that there are lots of amazing problems in complex equiangular lines, which we do not address at all, and there are some inherent difficulties. So, for example, Zollner's conjecture, which may be quite familiar to this audience, is about the existence of d-squared complex equiangular lines in d dimensions. But for upper bounds, there's an interesting problem here. If you restrict the complex, if you restrict an angle alpha and ask for a configuration of complex lines with angle, the absolute value of the inner product to be alpha, okay, we know that it's a most linear. So this is a result in Igor Bala's recent paper, but what should the leading coefficient be? So this seems to be a difficult problem because it has to go beyond the traditional spectral graph theory approach in the previous slide. More generally, you can view complex equiangular lines as real two-dimensional subspaces, but with a complex structure. If you forget that complex structure, you can just ask about configurations of k-dimensional subspaces in RD with given pairwise angles. Even here, I'm stating the problem very vaguely because what does it mean to the angle between two subspaces? There are lots of interesting notions and lots of interesting problems here. Okay, so let me summarize. We saw two results. One has to do with equiangular lines with a fixed angle. Here we solve the problem for fixed angle in sufficiently high dimensions. We tell you what is the maximum number of equiangular lines. And a key step in the solution is the following theorem about sublinear eigenvalue multiplicity of bounded degree graphs. Okay. Let me stop here.
Okay, so is there any question for Yufei?
I'll ask one silly question. I'm always responsible for the silly question. Thanks for the talk. Can you just comment on the discontinuity relative to alpha? So we know that we can't just change all the angles at once, but it seems to me that you also give yourself the freedom to increase the dimension dramatically in changing the angle by a tiny bit. These constants, the constant in front of D is a function of alpha and can be completely discontinuous, I imagine, as a function of alpha. Can you comment on that?
Yeah, that's a great question. So most of the argument here is continuous, but there's one step which is not, which is that we have to understand what is the smallest graph with top eigenvalue as given, and that's an algebraic property. Right? That's an algebraic property of alpha, and so that is inherently discontinuous. And it's important that we have that step because otherwise you cannot possibly get the answer. Right? So for approaches such as linear programming and maybe traditional inequality approaches, unless you can get to a point where you can say something algebraic, you're not going to be able to get the answer.
Yeah, those approaches are all continuous relative to alpha.
Okay, so any other questions for Yufei?
I have a quick question. I don't know if this is interesting, but you talked about Cayley graphs, and that in a Cayley graph of an abelian group, the second largest eigenvalue can't have a large multiplicity.
That's right.
Why is that?
Yeah, so that was a theorem. So let me go back to the slides. So this follows from this nice work here of Liam and Karachev. So they showed that if you have a Cayley graph that is non-expanding, then the second largest eigenvalue has to be small in multiplicity. And so so abelian groups cannot be expanding.
What about the complete graphs? I guess it's a
So here I'm restricting
that's a
myself
trivial
to down the
example.
degree. Yeah, down the degree.
Okay. Oh, okay. Yeah. Right. Okay, cool. Thanks. It was a really nice talk. Thanks for the talk.